What did you get, Charlie Brown?
I got a rock. I got a rock. Rock. I got a rock. 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 I got a rock. I got a rock. I got a rock. Rock.
What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock.
What did you What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock. Got a rock. 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 I got a rock. I got a rock. 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 I got a rock. I got a rock.
All right, so to continue from what we were doing last time, we were looking at various applications of DFS and BFS, and we left off with bipartite testing, where a graph is bipartite if you can partition its vertices into two different partitions so that the edges go back and forth between the two partitions and not within the partitions. So I think I've got let's go back over here to these examples here, like a C4 is bipartite. A C5 was not bipartite because, and then this is what we derived, that the observation that if we've got an even length cycle, we're okay, but if we've got an odd length cycle here, we're not okay, right? So what I wanted to do was to design really quickly an algorithm to do that. And you can either use DFS or BFS, it doesn't really matter. But the key here is to basically implement this coloring scheme, right? We're gonna go ahead and go with red and blue throughout. But here's breadth first search. This is the same breadth first search that we've already developed. What I wanted to do is I wanted to augment that and change that a little bit so that it's good for bipartite detection. So now remember that we initialize the algorithm by creating an empty queue here, marking the initial vertex here, which we're given arbitrary vertex, it doesn't matter. We color it gray that we visited it, we enqueue it, and then we proceed, right? We look at all of the neighbors, And then the neighbors of the neighbors, and then the neighbors of the neighbors of the neighbors, etc. While the queue is not empty, we look at the thing at the front of the queue. And then we look at all of the neighbors of that thing, right? Yeah, go ahead.
Do you need to mark discovery time? Because we never use it.
It depends on what your application. So if you end up using it as in an application, then yes. But if not, then for example, this one we won't be. So I'll omit that part. In fact, I've covered up everything right there, like right. That if it's white, then we increment our counter, we mark it, and we continue and move on. So what we're going to do here instead is we're going to use this algorithm to determine whether or not it's bipartite. So for each element in the neighborhood, if it's unvisited, actually before we do that, let's go ahead and suppose that we've already colored these vertices, right? So for example, up here, we'll go ahead and start out with, we'll use red and blue because that's what I've set it up for, up there for, right? And so with our initial vertex here, instead of coloring it gray, let's go ahead and color it blue, right? And then all of its neighbors will color red, all of the neighbors will color blue, and we'll alternate back and forth just like we did over here in this demonstration. And our check here will be if we have a gold vertex or a blue vertex or a red vertex or whatever, and we look at its neighborhood and we see another one of the same color, then we know immediately that we can stop and say that it's not bipartite. Okay? So we'll go ahead and start out with blue here. All right? Now, within this, what we're going to do is we're going to say, grab the color of that vertex, right? X dot color. And this is the current color of that vertex. Can I zoom in here? And let's erase that stuff and write a little bit more legibly here. So C will end up being the color of X. Okay? So that's my color. And now what I'm going to do for, I could have done that up here, I guess. I could have put that up here, but I'll go ahead and leave that since it's only, it's going to end up being the same color over and over and over again. But for each element in the neighborhood, what we're going to do is we're going to color Y. Actually, let's go ahead and make a check first, right? If Y dot color is equal to C, then we know that it's not bipartite. At that point, you can stop the algorithm and return false, right? Because you don't need to look anymore. You found a red vertex with a red neighbor, right? So you know that you have a cycle of length of odd length, basically, right? Otherwise, if it's not yet colored, right, then color Y with the opposite of C, right? So in other words, red to blue or blue to red. And then NQ it, right? It's Q dot NQ Y, right? If it's not yet visited, right? And so that takes care of it. If there's no, if there's already a color, then it doesn't matter if it's the opposite color, then you're good to go, and don't NQ it. Otherwise, you color it with the opposite color, and then you NQ it, and then you move on, right? Now, this is a high-level detail, right? The low-level details here would be worked out with whatever actual code that you write. I don't remember whether or not I asked you to do bipartite in the handout or in your assignment this Friday. What is it for this Friday? DFS, BFS, and anything else? I think maybe connectivity. Like this is connected to that, that's connected to that. Or maybe it's components, right? That this is a connected graph or not, and this is the number of connected components. But this would be very, very easy to do with either DFS or BFS. In this particular example, we've used breadth first search instead. Okay? All right. What I want to do with the rest of our time is talk about another way of augmenting graphs before we get into minimum spanning trees. Condensation graphs. So a morphism is a mapping from one graph to another graph such that the mapping preserves I can't spell that out. Preserves some structure. Okay? So the structure that we're going to be interested in, at least for this discussion today, is connectivity, right? So a homomorphism is a mapping from one graph to another graph that preserves connectivity, right? In other words, edge connectivity. So what I'm going to do here is I'm going to take a directed graph. Our goal here is to take a directed graph and simplify it. Simplify it to its core connectivity. And what I mean by that is two vertices in a digraph. This is a directed graph. That's a portmanteau of directed graph. So you take just digraph, right? Directed graph. Two vertices in a digraph are strongly connected if there is a directed path from one to the other and vice versa. Now, why would this be a good structure to have? Because if you're mapping or if you're modeling a network, if you start at a particular vertex and you need to get to another vertex, can you do that? That's connection one way. But then can you get back to where you came from, right? Can you have a cycle, right? If you're talking about people who can communicate to each other, A can communicate to B, but can B communicate a response back to A, right? So for example, here's a digraph. A can talk to D, right? But also A can talk to G, right? How? By communicating to D first, and then then D can communicate to G. Can you go backwards though? Can you go from G to A here? No. A is called a source. A is a source vertex, right? That it only has outgoing edges. What's the opposite? The opposite is a sink. F is a sink vertex. Why? Because the only edges to it are going into it, right? Are incoming edges. Once you're in F, you're sunk, right? You're in a sink. You can't ever get back out of it anywhere in the graph, right? So we have some connections here. A can talk to D. D can talk to G, but we can't go back to A. So A and D and G are not strongly connected, right? They're connected one way, but they're not connected both ways, so they're not strongly connected. So my goal here is to take, and this is the graph that we'll use as an example. Our goal is to create a smaller condensation graph of a directed graph. A smaller graph that preserves strongly connected components. Right? So in other words, we're going to take all of the edges or all of the vertices that are strongly connected with each other, and we're going to consolidate them or condense them down to a single edge. This is why it's called a condensation graph. You're taking something large and you're condensing it into something smaller that has the same basic connectivity properties. Okay, so here is my process, right? And we'll run through the process in the in the example graph here. You perform a DFS, noting the finishing time. So this is where those finishing or discovery times come in if it's a particular application. You compute the transpose graph, which is basically just taking all the edges and reversing them. Because if it's an adjacency matrix, right, then if you take the transpose of that matrix, it reverses all of the orientations of all the edges. That's why we call it transpose. And then you perform another DFS in order of the finishing times, and every time you start over, That's a new strongly connected component. Okay? So let's go ahead and do step 1 here on this graph over here. Okay? Let me go ahead and erase that stuff so that it's out of the way. So a DFS, and it doesn't matter where you start. We'll go ahead and go in lexicographic order. I'll start at A here, and discovery time of 1. Okay? If we're going in lexicographic order, where do we go next? B, right? With a discovery time of 2. Right? Remember, this is DFS, depth first search. If we go in lexicographic order, we can go from B to C. Right? There we go. That one. And that's a discovery time of 3. Where do we go from there? We have 2 choices, right? We could go, actually we got 3 choices, right? We could go back to B, but it's already been discovered, so do we return to it? No. We could go to D, or we could go to F. Since we go in lexicographic order, we'll go over to D. Right? I'm just keeping track of our actual DFS. Right? From D, we go to G. Discovery time of 5. And then finally over to F. Right? There. Once we're in F, we're in a universal sync, so we now have to start backtracking. We finish F at timestamp 7. There are no more choices for G, so we finish it at 8, 9. Once we're in C, we're done with everything. There are no choices in C because we've already colored F black, and we've already colored D black. 10, and we backtrack to B. Now, we don't finish B yet. Why? Because we can still go to E. So we explore that, and our next timestamp is 11. That's now finished, so 12, 13, and 14. Making sure to note that edge is what we traversed for the DFS. All right? That's step 1. Note the finishing timestamps because that is that's what we're going to use in this particular application. Okay? Now we need to compute the transpose graph. Right? The transpose graph is going to be exactly the same graph. Oops, let's go with black here. A, B, C, D, E, F, and G. But all of the edges are going to be reversed. So going from D to A, going from B to A, and going from E to A. Right? They're all going to be reversed. Going from E to B. There we go. And then these, it doesn't really matter. I'll draw them reversed. But since they were strongly connected pairs already, right, then it really doesn't change anything. Right? If you have a symmetric graph, like an undirected graph, the transpose is equal to the regular is equal to the original adjacency matrix, and so those 2 entries will be across the diagonal, and they'll both be 1. Right? Going from C to E, going from F to C, right? And then D to C, right? Over to F, or G, excuse me, and then back and forth here. It will reverse them so that they're like this. Did I get everything? I think so. All right. So now that we've got that transpose graph, what we need to do is perform another DFS in order of the finishing timestamps. Each time that you start over, you create a new node. Okay. Starting with the, I forget now. Where would we want to go? I don't think it's going to matter, but we'll go ahead and go in decreasing order. Right? Okay. So let's go ahead and do another DFS. This is the transpose graph. And we'll do a DFS on, usually we call it G sub t in descending order. According to the timestamp, the finishing timestamps up here. Now remember that the finishing timestamps are the second number. Right. So which one should I start at? Yeah. F. So let's do and I'll do it in red down here. Let's start at F here, right? And I'll do a DFS on this. What do I want to say? Do I do? I want to say no in ascending order. Or no, I said descending order. So what would I start at F? If it's descending order? A, right? Largest to least, right? Right. So yes. So there we go. We'll start at A. And we discover it at timestamp 1, and guess what? We have nowhere to go. So what do? We finish it immediately. Every time we start over, what we do is we create a new strongly connected component over here. Right? And I'm going to associate that with A. Right? That's done. The next one that we start out is, in descending order, is B. So we'll start here at B, timestamp 3. Well, we could go over to A, but that's already been discovered and colored black and finished. Right? So where do we go? Over to C. Oops. There we go. Discovery time of 4. Now where do we go? The only place that we can go is E, 5. And we could go to A, we could go to B, but that's black and gray respectively. So 6. We backtrack. Were there any more options at C? Nope. We backtrack. 6, 7, excuse me. And backtrack, and that's it, right? Then we're done with that iteration of DFS. So let's create another component over here. Yeah, I'll do it right here. And associate with that each one of the vertices that we successfully visited, B, C, and E. Now, I'll draw your attention to the fact of what we're doing here. A, by itself in the original graph, is its own strongly connected component. Because from A, you can reach many things, but can you reach A from anything? Nope. So it's all by itself over here. Well, what about B, C, and E? You can go from B to C, right? And what else? You can go from B to E, and from E, you could go to C, right? And you can go back to B. So this entire thing is a strongly connected component. Right? Let's continue. What's next? So I took care of this, I took care of this, and I took care of this. In descending order, it's going to be next, D. And my counter is now at 9. Right? From D, I can go to G. I could go to a lot of things, but they're all discovered already, right? This is done, this one's done. So I go to G. From G, can I go anywhere? Nope. So 10, I start backtracking 11 and 12. Right, there we go. And I'm done with that strongly connected component. So D and G. I start. Am I done? I'm not done yet because F is not yet discovered. So I start over with that and 13 and 14 because my other options are already visited and processed vertices. So we end up with F as its own strongly connected component. For the same reason that A was its own strongly connected component, but for opposite criteria. Right? This is a universal sink. So the source is by itself, the sink is by itself, and we've got these other components that are all strongly connected. Now, the condensation graph is not yet done. From A, we can get to anywhere else in the graph, right? So let's go ahead and draw some arrows here. From A, I can get to, say, B, C, and E. How? Go to, you go to B or E, but once you're there or there, you can go ahead and traverse around this entire strongly connected component however you want, just by following this cycle right here. Okay. What about B, C, E? That strongly connected component. Can you get to F? Yep. Just by going through, what was it, C? Right. And then what about DG? You can get there as well. Right. And then from anywhere else, you can get to from DG to F. There we go. And from A, of course, you can go over to F, but transitively, you can already take care of that through that other group over there. Right? So this is the condensation graph. Now, why would that be? You can draw this if you want. I'll go ahead and put it like that. That you could get there. Say what?
It can also get to V.
Oh, okay. Through.
The top.
Yeah. I will leave it like this because. Oh, actually, yeah. Okay, I'll go ahead and draw it because you can go from directly from A to D, and so I'll draw that there. But I'll go ahead and leave off this implicit arrow right there, right? So there's your condensation graph. Now, why would that be useful? Graph topology, right? You're modeling something, right? You're modeling relationships. Can you simplify those relationships? For example, communication networks, right? If you're trying to go communicate from node A to node F, right? Can you do it first of all? And yes, if you go through this group over here, right? All you have to do is relay your communication to one of these three, or whatever your entry point is in the original graph, and you're assured that you can get over here, right? It basically simplifies the graph. It takes you could have a graph with 1,000,000 vertices. If you can have the same topology by simplifying it down to say 5 vertices, right? Then that would be huge computationally, right? Then you would be able to route stuff a lot easier, or potentially, or do simple graph algorithms a lot simpler on an input that's much smaller. And so that's that's the point of having a homomorphism. A homomorphism is a mapping from one graph to another that preserves some edge connectivity. Okay. Another way of doing this, not with the condensation graph, but another way of doing a homomorphism is through what are called minimum spanning trees. Right. So given an undirected, weighted, and connected graph, edges have weights. Right. You want to create a spanning tree of minimum total weight. Right. Well, what's a spanning tree? A spanning tree is a tree, a subset of the same vertex set, but a subset of edges that leave the graph still connected but acyclic. Right? That's what a tree is. Okay. Many spanning trees may exist, but you want to find the best one, the one of minimum weight. Even then, there may be more than one minimum spanning tree, or MST. Okay? So let's just take a look at a really quick example here. Doodling with my kids over the weekend. Let's see. I want graphs used. Let's go with. There we go. There's a graph. First of all, is that a tree? Clearly not. Yeah, there are lots of cycles. So let's just go ahead and come up with, I don't know, a random tree here. Let me go ahead and start highlighting these edges. Let's go ahead and go with that one, that one, that one, that one, that one. Undo that. Let's see. That one. Okay. So in other words, the graph looks something like this. There we go. And these two down here. Now, first of all, is that an acyclic graph? Yes. Is it a tree? It's a collection of trees, right? It doesn't span the graph. Right? It doesn't connect to the graph as it originally was. I could add this one or this one, and then it would connect it. So let's go ahead and add that one. There we go. Now that's a spanning tree. Okay. What is the weight of that spanning tree? 5 plus 8. I have 18 in my head now. Plus 15. That's going to be 33. Plus 11 plus 8. So 44. And then 52. Right? So that would be 52. Can we do better? Yeah. How? Well, let's not do 8 right there. Instead, let's go ahead and go over here for 6. And now we're down to 50. Can we do better? Certainly, right? So how do we go about finding the minimum? There are an exponential number of possibilities. There's no way that we can go ahead and try them all. So what we need to do is we need to be more systematic about it. Okay. So there are lots of spanning trees. And by the way, if you have a disconnected graph, note, if you have a disconnected graph, it is still possible to compute a minimum spanning forest. 1R, I think. And that's what you're going to have to do. Not in this week's assignment, but next week's assignment. When you do implement a minimum spanning tree algorithm, we're expecting a minimum spanning forest. Because if it's disconnected, you'll have to restart it, right? Just like DFS, BFS, if it's disconnected, you may have to restart those algorithms. You'll have to do the same thing here. Right? We're going to actually look at 2 different algorithms. There are actually like a half a dozen, but the 2 standard ones that are looked at are Kruskal's and Prim's. Kruskal's is really, really easy because it's a greedy algorithm. It makes a locally optimum choice to develop a globally optimal solution. Right? The basic idea is to be greedy about it. You consider edges in increasing order of weight. Right? You add them if adding them would not induce a cycle. Right? That is, create a cycle. Right? Otherwise, you don't add them. So step 1 would be to take all the edges and sort them. So let's do that. Actually, let's go ahead and sort them. Right? So edge. What's the first one that I would put? We'll sort them as we go, so I don't have to write them all out.
Smallest to biggest.
Smallest to biggest. Least amount of weight to greatest, because you're trying to minimize it. But that's a good question. What if you went in the opposite order? Great to the smallest? Yeah, then what would you be creating? Not a minimum spanning tree, but a maximum spanning tree, right? That's called the dual. If you ever have an optimization algorithm where you're minimizing something and you flip it so that you're maximizing it, that's the dual of the optimization problem, D-U-A-L. Right? So which one do I consider first? Well, there are 2 of weight 5, right? So break ties arbitrarily or go with lexicographic order. A, D, and the weight of 5, and CE at a weight of 5. So when I'm starting out, right, none of these edges are in my tree yet. Yeah, go ahead.
How do you break ties arbitrarily? Do you do like random numbers?
Well, I'm doing it lexicographically, so random is fine. But I think that in practice, if you were to do random in an actual program, that'd actually be more work than just going lexicographic, right? Or another way to do it randomly or non-deterministically is if it's a set, then whatever internal iterator you iterate over the elements, you just let that do it. Right? Okay. So since I'm starting out here, there's been no edges that have been added. So adding this first one is not going to definitely not going to induce a cycle. So let's go ahead and just add it. Right? And that's my tree so far. My tree is all of these vertices that are disconnected, and now these 2 vertices that are suddenly connected. Right? So let's go ahead and record as we're going along, add or not, question mark, and I added it. Added. Likewise, I'm going to add the second one as well because it's way on the other side of the graph and it will not induce a cycle. Right? What do I consider next? I see one that's of size 6. Oops. D and F. Is that the only one? I think. Right? So now adding this edge here would mean that we're not going to induce a cycle. So I'll go ahead and add it. Added. And record that as well. By the way, how am I detecting whether or not it would induce a cycle? Do DFS, BFS to detect cycles, right? You would start out with your vertex set being all the same vertices, and then an empty edge set, and you add an edge and ask, well, is it acyclic? Yes, okay, keep the edge. Oh no, adding that edge induced a cycle somehow, right? Then take the edge back out and continue with the next edge. What's next? Sevens. So A, B, and BE. Right? 7 and 7. There we go. So do I add AB? Yeah, that's not a cycle yet. Do I add BE? Yep, still no cycle. So added. I'll go check mark for added, added. What's the next thing I consider? BC and FE, or EF, right? If I'm EF, and that's 8. And what was the other one? BC? 8. Now, if I were to add this one, what happens? Cycle. If I were to add this one, what happens? Cycle. So therefore, nope, I didn't add that, I didn't add that. All right, we move on to the next tier. What? BD at weight 9 and EG at weight 9. So do I add that one? Nope, that would induce a cycle. So no. Do I add this one? Yep. So added, yes, check mark. Do I need to continue? No, why? How, well, yeah, say what? Every vertex is connected. How do we know that? Well, other than looking at the picture. How many edges have I added so far? 1, 2, 3, 4, 5, 6. How many vertices are there? 1, 2, 3, 4, 5, 6, 7. Right. A spanning tree is necessarily of a graph with n vertices is necessarily going to have n minus 1 edges. I don't need to consider the rest of these at all. Once you have as many edges as you need, you stop. Now, the same is not true for a forest. With a forest, you need to make sure that you are actually connecting those components. So you may need to go all the way to the end before you're done. Right? Or you do something more sophisticated to say that, well, this component over here is now connected, this component over here is now connected, and I know that there's not going to be any edges between them, so I'm done. Right? That's a little bit more complicated, and I wouldn't recommend it. Right? But otherwise, we're done now. What's the total weight? I see 5, 11, 18, 25, 30, 39. Is that correct? Check my math, please. Yes? Okay. Excellent. Then we're done. Right? 11, 18, 25, yeah, 39. Yeah, what? Okay. All right, good. We're good. All right. That's crucibles, right? What didn't I add? Yep, those would induce a cycle. I'm done. As soon as I know that I've got enough edges to span the tree, then I'm done. Right? So step 1 in this algorithm is to what? Sort the edges, right? So crucible. Right? My input is going to be a weighted graph, undirected graph G equals V comma E. Okay. My output will be a minimum spanning tree of G. because there could be many other spanning trees. For example, I don't think that there are any in this in particular case. This might be unique, but there you can come up with very easily. You can come up with examples where there are multiple minimum spanning trees. For example, this graph, A, B, C, and I'm going to put weights equal to 1, 1, 1. How many minimum spanning trees are there? There's this one, there's this one, and there's this one, right? Because all you have to do is choose an edge and throw it out, and that's a minimum spanning tree. Okay, so what's my first step? Sort E in decreasing order. Now let's go ahead and analyze this as we go along. If you have to sort the edge set, what's the complexity there?
Go through every edge.
Every edge, and how many edges are there?
Depends on what end.
Yeah, it depends on the density of the graph, but usually we use what variable to denote the edge set, the size of the edge set? M, right? So sorting a collection of size M is going to be what? It can be M squared if you do a bad sorting algorithm, right? Like selection sort or something. Can we do better? M log M. Yep, that's quick sort, merge sort, Tim sort, whatever. Right? Now, if you consider M to be, or if you consider M to be your input size, then great, you're good to go. But what if you decide that you want N instead, the number of vertices to be your input size? What is the relationship between N and M? All right. M is going to be order N squared. So plugging this in with respect to N, what do we get? Order N squared log N squared. What happens to that square in the log? Yeah, well, it goes away, right? Because it's a constant out front. All right. So you could say that this is already going to be quadratic, right? Plus a logarithmic. Right?
If it's a complete.
Well, even if it's a dense graph, it doesn't have to be a complete graph. It just has to be that M is on order N squared. Right? So either one of these perspectives is correct. Okay, and remember it's big O, so it's a worst case scenario. Okay. Next, what do we do? 2. Let me go ahead and create an edge set here called the tree edge set. Tree edge. Here. I'll start out with an empty set here, and this is the tree edge set. Okay. Now I've got my set that I'm going to add things to, add to, add to, add to. Right. What's my condition for stopping? Okay, while the size of the tree set, tree edge set, is strictly less than n. Will it ever be n? Remember this n here was 7. 1, 2, 3, 4, 5, 6, 7. But the size of the edge set that we ended up with was 6. So n minus 1. Yep. Yeah, well, I mean, you have to get it so that the number of edges in there is n minus 1. Once you've hit n minus 1, you're done. You can break out. Right? So while you don't have enough edges, what do? You consider the next edge in the sorted set, right? So E will be the next edge. Right? And what I'm going to do is I'm going to create another graph here, G prime, which is going to be all the vertices as well as the edges that we've already taken and E. Right? So this is the edge set of the tree edge set that we've built so far. I'm just taking the union and I'm adding E to it. And I check if G prime is acyclic, then I will make that addition permanent, right? E sub t will be e to the t union e, right? So my annotation here is add e to the graph, and if it does not induce or create a cycle, keep it. Right? That's it, right? Get down to the end and you've created a minimum spanning tree. Now, if you've broken out of this while loop here, and this is still not you need another condition, right? If you've exhausted all of your edges and you still haven't built a minimum spanning tree, then by implication you've built a minimum spanning forest. And so you do need another condition potentially here, right? Some other condition. I'll leave that as an exercise for you for minimum spanning forest. Okay? In other words, the condition is just simply going to be if you have no more edges to look at. Okay? At the end, what you do is you output your minimum spanning tree, T, which is the same vertex set as before, but ET. Right? Remember, the same vertex set as the original input graph. Okay? Now, again, depending on how you break ties, you could end up with a completely different graph. But the minimum weight is going to be the same. What about the complexity of this part right here? In fact, let me go ahead and cut and paste that. Come on. Copy. Paste. So we'll zoom in on this one part right here. Okay? So, I don't know. What about this? I mean, this is just necessary for the control structure of the algorithm. You're just going to have some iterator over your set that you sorted. This is just going to be creating another graph, so who cares? But what about this? This is the elementary operation right here. Testing whether or not something is acyclic. Right? So if I were to use DFS on this, what would it be? It's going to be order n plus m, or order n squared if m is your, if you want to do it just in terms of n, right? This is going to be order n plus n squared, right? Which is order n squared, right? How many times are you doing that potentially? M, n or m? N as in negative, m as in, what is NATO? Maple syrup, I guess. What is it? M? Well, yes, y, right? This entire thing here is going to be order m. Why? You potentially have to check every edge. What if it's that last edge that you get that gets you your last edge that you want, right? So in other words, since this is done on every iteration of this, what overall what do you have? Order m times all this stuff right here, n plus m, which is order m squared, right? And I'll just leave it like that because that's the highest order term. And like you said, if it's in terms of n, order n to the fourth. That doesn't sound all that great. Now, we're stuck with the sorting right here, right? So we're not going to improve on that too much. But can we at least get this part down to where it matches that sorting? To do that, we're going to need another data structure, right? And for that, we'll wait until next time.
So you mean get the part where to find it if it's acyclic?
Yep, we're not going to use DFS. We're going to use something else. We're going to use Well, I'll wait for next time.
Can we do that on the, again,
So, well, for your programming, and the minimum standing trees, I think, are next week, not this week. Don't quote me on that, though. But for your programming, I would suggest, I mean, you're not going to have graphs that difference is going to matter. So I would suggest just programming it straightforward, right? Unless you want to use the code that we're going to develop for the data structure that we're going to look at. All right, next time.